Okay, so we've started out this chapter looking at homogeneous and non-homogeneous linear equations. We've talked mostly about theory. The last section in reduction of order, we talked about if you have one solution, how do you develop or find a second linearly independent solution. Starting in section 4.3, we're actually going to be solving. So we're going to start out by solving homogeneous linear equations. And then we talked about with non-homogeneous, you have to solve the homogeneous one first. So once we get to non-homogeneous, you're going to still have to solve the homogeneous one first. And then there will be methods to solve the non-homogeneous part to find your particular solution. Okay, let's jump into some background of things you learned in BC that you probably forgot. First one, I'm sure you know, we're going to need to remember complex numbers for this section. So a complex number remembers of the form a plus bi. It has a real part, it has an imaginary part. We can graph these complex numbers in what's called the complex plane. This you may not have seen before. X-axis is considered the real axis. Y-axis is considered the imaginary axis. So you'd go over A and up B. This is your R, this is your theta. A few things to remember. R squared is equal to A squared plus B squared. A is equal to R cosine of theta. B is equal to R sine of theta. Okay, any complex number, bless you, could be written in the following form. Let's say that we call it Z. It could be A plus BI, or another way to write this is R cosine theta plus R sine of theta times I. If we factor out the R, we have cosine of theta plus I times sine of theta. This is abbreviated as R cis theta. So this has the same meaning as what's above. That's the first thing I need you to remember. Second thing is series. Following series, n equals 0 to infinity of x to the n over n factorial. What is that the series for? E to the x. So that's 1 plus x to the first over 1 factorial plus x squared over 2 factorial, etc. We also have the sum from n equals 0 to infinity of negative 1 to the n over 2n factorial x to the 2n. What is that a series for? Cosine. And then last one I want you to remember is the sum from n equals 0 to infinity of negative 1 to the n for 2n plus 1 factorial x to the 2n plus 1. You could probably guess this is the one for sine of x. This gets all the odds. Promise you we are going to do something with this. I'm not just showing it to you for fun. Okay, here's where this becomes helpful. We're going to let x be equal to I theta in e to the x. So we get e to the I theta then. We're going to do this, replacing every x with I theta. So we get 1 plus I theta plus I squared theta squared over 2 factorial plus I cubed theta cubed over 3 factorial, and then you're going to keep going. Okay, what you should notice is that every other term is real and the remaining terms are imaginary. So this term is going to be real. This one, I squared, is -1, so this is also real. This is imaginary, this is imaginary, so they're going to alternate. So it's helpful then if we put the real parts together and the imaginary parts together. The real parts, 1 minus, because I squared is -1, theta squared over 2 factorial, plus theta to the 4th over 4 factorial. If we have all the imaginary parts, we have theta minus theta cubed over 3 factorial, plus theta to the 5th over 5 factorial. So these are all the reals, these are all the imaginaries. This first part, all the real parts, or all the real terms, that's the series for cosine of theta. The second one is the series for sine of theta. Okay, so what does that tell us? That tells us that e to the I theta, another way to write that is cosine of theta plus I times sine of theta, which we already said before we abbreviate as cis theta. This is a very famous equation. It's called Euler's formula. Not Euler. Okay. That's all the background. This is going to help us now when we start solving. Okay, we are going to start by looking at a homogeneous linear differential equation of first order. So we know dy dx plus ay equals 0 has the following solution. You all could solve this. We're not going to go through and solve it, but if you did, you would find that y is equal to c1 e to the negative ax. So the question that arises then is, what about higher order equations? So what if we're looking at the equation a y double prime plus by prime plus cy equals 0? This is what we're going to solve today, is an equation like this. A few things to notice. It's homogeneous because it's equal to 0. It's linear, and all of the coefficients are constants. So a, b, and c are constants. They are not functions of x. Okay, we could probably take an educated guess as to a solution, just based off of the form here. Constant, we don't care about. So we are going to guess that y equals e to the mx might be a solution. Okay, we're going to find the first and second derivative, plug it into our equation, and see if this is in fact a solution. Y is equal to e to the mx. Y prime them is me to the mx. Y double prime is m squared e to the mx. Substituting those into our differential equation, we get a m squared e to the mx plus b m e to the mx plus c e to the mx. We want to know if this will equal 0. If it equals 0, e to the mx is a solution. If it does not equal 0, not a solution. Factor out that e to the mx. So we get am squared plus bm plus c. Okay, we should be able to see that e to the mx is not going to be 0. So if e to the mx is a solution, then m must be a root of am squared plus bm plus c equals 0. So in order for e to the mx to be a solution, we have to be able to find a solution to this equation. Okay, this is a very important equation. This is called the auxiliary or characteristic equation. And you should see that it looks exactly like our differential equation, except y double prime is m squared, y prime is m, and then y doesn't show up. Okay. With me so far? Okay. If we are solving this quadratic, there's going to be 3 separate cases that could come up. The first case is you have 2 distinct real roots. You could have 1 real root that's repeated, or you could have 2 complex roots. So each of those are going to look different in terms of the solution. So we're going to look at them separately. First case is that the auxiliary equation has 2 real roots, m1 and m2. If that's the case, we have one solution, that's e to the m1x. We have another solution, e to the m2x. Okay, we've talked about before, we want to know if we can form the general solution based off of these 2. When can you take 2 solutions and make a general solution? Not just another solution, but a general solution. What has to be true about the solutions you have? They're linearly independent, and how do you check that? The Wronskian. Okay, so now we're going to calculate the Wronskian of these 2. Okay, so when we do this, we get m2 e to the power m1x plus m2x minus m1 e to the m1x plus m2x. Factor out the e. What do we care about the Wronskian? Like, what are we looking for? If it equals 0. That is not going to equal 0. What about this? Does it definitively equal 0? Could it equal 0? Or does it definitively not equal 0? Okay. Back here, I said it, I didn't write it. Do you remember me saying that these are distinct roots? They are different roots. Okay, so in this case, m1 does not equal m2, so this is not going to equal 0. That tells us that y1 and y2 are linearly independent. What comes after linearly independent? What is your next conclusion? We're looking for the general solution. So we have 2 solutions that are linearly independent. Can we jump right to the general solution? Yes, fundamental set. Thank you. So these 2 solutions form a fundamental set. Therefore, we have a general solution. Our general solution then is y equals c1 e to the m1x plus c2 e to the m2x, and that's by superposition. Okay, so that is the first case. Now, how will you know if this case applies before you even start solving the auxiliary equation? Is there a way to tell that a quadratic has two distinct real roots without solving it? Starts with a D, yes. The discriminant, the thing under the square root. Woo! Okay. So that's the first case. Second case is we have one real root that happens twice. Okay, if this same solution happens twice, it has to be real. You can't have an imaginary solution that happens twice because they always come with their conjugate. Okay, so then we know that one solution is e to the mx. So I'm just going to call these both m. We obviously are not going to use a second solution that's exactly the same. Those wouldn't be linearly independent, so we wouldn't be able to find the general solution then. How do we find a second solution if we know that the first one works? What's that called? Reduction of order. Okay, but luckily, we don't have to do the entire reduction of order process. We can just use the formula. So remember that the differential equation we had was a times y double prime plus b times y prime plus cy equals 0. Can I use the formula currently? No. Divide by a. So y double prime plus b over a times y prime plus c over a times y. Okay. So now we're ready to do the formula. y2 is equal to e to the mx times the integral of e to the negative integral of b over a dx over e to the 2mx dx Okay. Quick note. It's not helpful to have this b and a here. We want to try to get rid of as much as we can. So quick note. If we have one real root, what do we know about the discriminant? Discriminant equals 0, which tells us the rest of the quadratic formula, so the negative b over 2a, is what m is equal to. If I multiply the 2 over, 2m is equal to negative b over a. So this negative b over a I can replace with 2m. Well, this ends up being pretty convenient. In the numerator, we have e to the 2mx. The denominator, we have e to the 2mx. So we get e to the mx times the integral of dx. Our y2 then is x e to the mx. Reduction of order guarantees that you have two linearly independent solutions. So this will be linearly independent with our first solution, forming a fundamental set, and then our general solution. So here's the general solution for this case. y is equal to c1 e to the mx plus c2x e to the mx. Okay, I don't expect you to go through the derivation for every case. If I were you, I would just memorize them. So just memorize these three cases. Okay, what case have I not talked about so far? Or have we not talked about? When we have two complex. And it's important to remember that they will be conjugates. How do you know that the auxiliary equation will have complex roots before solving it? Discriminant is negative. Okay, so let's let M1 be A plus I times beta. M2 then will be alpha subtract I times beta. From case 1 then, since we have two distinct roots, we can write our general solution as C1 e to the alpha plus I beta x plus C2 e to the alpha subtract I beta times x. Now, this is not helpful. We don't want to have a general solution that has imaginary parts in it. So we want to see if there's a way we can write this in terms of real functions. So without the imaginary parts. We are going to need this later, so I'm going to call it star for when we need it later. Okay, at the beginning of notes, before we started solving any of these, we looked at complex numbers and we looked at Euler's formula. So we're going to look back at that now. E to the I theta, we said was equal to cosine of theta plus I times sine of theta. That was Euler's formula. So we're going to see if that helps us at all with the imaginary parts here. So here that e to the alpha x, that's fine. Here the e to the alpha x, that's fine. The e to the I times beta x is our issue. From this first solution, e to the I beta x, so that's here and here, using Euler's formula, that's equal to cosine of beta x plus I times sine of beta x. That second solution is going to be e to the negative I beta x, which gives us cosine of beta x minus I times sine of beta x. Okay. So here's what I'm going to do. First, I'm going to add those two together, then I'm going to subtract them. If I add these two together, I get e to the I beta x plus e to the negative I beta x. You should see that those signs cancel, so we get 2 cosine of beta x. If I subtract them now, cosines are going to go away, and we get 2I sine of beta x. Okay, this you have to keep in mind. We're not using it just yet, but we are going to use it. Okay, you guys with me? Yeah. Okay. We're going to return to that star equation. For y1, so if we want to find y1, we are going to let c1 equal c2 equal 1. Okay, for y2, we're going to let c1 equal 1 and c2 equal negative 1. Then here's what we get, y1. both on the same screen. Okay, this will be equal to e to the alpha plus I beta times x plus e to the alpha minus I beta times x. Y2 is the same, but with subtraction. Okay. Y1. I'm going to factor out that e to the alpha x. When I do, I get e to the I beta x plus e to the negative I beta x. This is up here. It's equal to 2 cosine of beta x. This is really e to the alpha x times 2 cosine of beta x. So our first solution then is 2e to the alpha x cosine of beta x. Remember though, we don't care about that. We don't care about the constants. Our y2 from above, again we're going to factor out e to the alpha x. And when we do, we get e to the I beta x, subtract e to the negative I beta x. We already showed above that that's equal to 2I sine of beta x. Which gives us 2I e to the alpha x sine of beta x. Again, we don't care about that constant though. So finally, our general solution. Y is equal to C1 e to the alpha x cosine of beta x plus C2 e to the alpha x sine of beta x. More commonly, that e to the alpha x is factored out, and this is generally written as C1 cosine of beta x plus C2 sine of beta x. Okay, I wanted you to go through the derivation to see why each of these is the case. Like I said, though, I don't expect you to be able to do that. I would expect you just to memorize. Okay. We're going to look at a few examples now. Here is the first example. We are going to solve the following initial value problem. Y double prime minus 4y prime plus 13y equals 0. Y of 0 is equal to negative 1, and y prime of 0 is equal to 2. Okay, so first thing that we're going to have to do is solve the auxiliary equation. It's based off of this. So it'll be m squared, subtract 4m, plus 13 equals 0. Okay, you have a few different options here. Does not factor. You could complete the square or do quadratic formula. I'm going to do quadratic formula. So we get 4 plus or minus the square root 4 squared minus 4 times 1 times 13 all over 2. Underneath that square root, you get a negative 36. So we get 4 plus or minus 6i all over 2. So our solution then is 2 plus or minus 3i. So we can see that this relates to case 3. 2 is the alpha, 3 is the beta. So the general solution then, using this, y is equal to e to the 2x, c1 cosine of 3x plus c2 sine of 3x. So all that derivation looks really bad, but these problems are pretty short. Now, sometimes you'll stay there. Now, though, we need to use our initial conditions. Are you guys following me, or did I go too quickly for us? We're good? Okay, great. Okay, so this one, if I plug in -1, I get -1 equals e to the 0, c1 cosine of 0 plus c2 sine of 0. That is 0. This is 1. This is 1. So our c1 ends up being -1. So we now have e to the 2x times negative cosine of 3x plus c2 sine of 3x. Our next condition was y prime of 0 equals 2. We're going to have to find the derivative of this. You're going to use product rule. So we get 2e to the 2x, negative cosine of 3x plus c2 sine of 3x plus e to the 2x times 3 sine of 3x plus 3 c2 cosine of 3x. Plugging in a 0 for x, we get 2. This will be 1, so we get -1 plus 0 plus 1. That is 0, so we just get 3c2. This is a -2. If I move it over, I get 4 is equal to 3c2. So our c2 then ends up being 4/3. Our solution then is y is equal to e to the 2x times negative cosine of 3x plus 4/3 sine of 3x. Okay. Any questions before we keep going? I told you today's notes were long, so I did warn you. Okay, we have one more thing to talk about, one more example, and then we're done. Okay, next question is, what about if you have higher order differential equations? So right now, we've looked at homogeneous, linear, second order. Okay, to solve an nth order homogeneous linear differential equation of the following form. So this will be an nth derivative of y you're going to use the same approach. You're still going to solve the auxiliary or the characteristic equation. Yes.
Should that be an N with D? Or is it supposed to be a 2?
That's an n. Thank you. So here our aux equation will be a of n, m to the n, plus n minus 1, m to the n minus 1. You still have the same cases. Case 1 is that all roots are real and distinct, in which case your general solution is very similar to what we did before. Y is going to be equal to C1 e to the m1x plus C2 e to the m2x all the way up to Cn e to the mnx. Okay. Cases 2 and 3, I'm going to put together. If you have a root m1 that has multiplicity k, then your solutions are as follows. We have e to the m1x, x e to the m1x, x squared e to the m1x, all the way up to x to the k minus 1 e to the m1x. Your general solution then must contain a linear combination of those above solutions. So we'll have C1 e to the m1x plus C2x e to the m1x all the way up to ck x to the k minus 1 e to the m1x. That's not your general solution. Your general solution will contain that in addition to whatever other solutions there are. Okay. We're going to do one example of higher order than second, so you can see kind of the way to approach it. And then that'll be the rest of our notes. We have 3y triple prime plus 5y double prime plus 10y prime minus 4y equals 0. Our aux equation then will be 3m cubed plus 5m squared plus 10m minus 4 equals 0. Okay. This is a throwback to probably Algebra 2. How do you solve that without a calculator? Huh? Okay, can you factor by grouping here? If that worked, that'd be nice. What happens if it doesn't? Okay, guess numbers, yes. Are you just guessing any numbers at all that you feel like? There is a thing, yes. Do you remember your P's and Q's? What? You've seen this. I am fairly confident you guys have seen P's and Q's. Particularly because Brian basically said it without those words. If you remember, you find all the factors of P. Plus or minus 1, plus or minus 2, plus or minus 4. You find all the factors of Q, plus or minus 1, plus or minus 3. The possible roots then are P divided by Q. So we we have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/3, plus or minus 2/3, plus or minus 4/3. How do you figure out if it's a solution? Yeah, you're going to do some synthetic division. Isn't this so much fun? Okay, I would suggest starting with 1 and -1. Those are generally good ones to start with. So bring out those constants, 3, 5, 10, -4. Do you guys remember how to do synthetic division? No. Okay, first number you bring down. You're then going to do 1 times 3, which goes here. Then you'll add. So we get an 8. 1 times 8 is 8. You're going to add 18. 1 times 18 is 18. Add, you get 14. Was 1 a solution? No. How do you tell? The remainder. Okay. I am not going to go through and guess and check for you. I'm just going to tell you one that works. Is that good with us? Great. 1/3 ends up working. Okay, so what that leaves us with, m minus 1/3 is one of the roots. And then we have 3m squared plus 6m plus 12. That second one you can try to factor. I'm going to tell you it doesn't factor, so you're going to use the quadratic formula. Are you okay if I just tell you what it ends up being? Okay. It ends up being -1 plus or minus root 3i. Okay, so finally, that general solution then is going to be the following. We're going to take care of that 1/3. So this will be C1 e to the 1/3 x. And then we have this imaginary part. So it'll be e to the alpha x, so e to the -1 x. And then we have C2 cosine of root 3x plus C3 sine of root 3x. All of that is the general solution.